Hi there, my name's James, and in this video I'm going to talk you through a gesture-controlled gaming setup I built in Python using a webcam, computer vision, and some AI. The goal here was to build something that mimicked consoles such as the Xbox Kinect, which for those who don't know is a camera extension to the Xbox, which allows users to control games through a natural user interface. This is basically where the camera films you whilst you're playing and then uses your movements in place of a controller. The result is two games, both of which use hand gestures to navigate through a series of user menus, instructions, and also to play the game. The first is a spin-off of Flappy Bird, where the goal is to navigate through a series of moving gaps using your index finger. And the second game is a speed trial of how many hand gestures you can match to emojis within the time limit. And this is a bit more advanced since it uses some AI to determine which gesture the user is making. We'll build our own pipeline, dataset, and model to do all this. The first challenge you'll face if trying to build something like this is the hand detection. We need a way of accurately detecting multiple landmarks on a hand displayed through the webcam. MediaPipe offers a great solution to this. It's a pre-trained model designed to pinpoint 21 X and Y coordinates on a hand that appears in any image. Not only is the MediaPipe model robust, it's fast too. In fact, I can run it quite comfortably on my Mac Air M1 chip at around 20 frames a second, which makes it ideal for our goals. MediaPipe can run so fast because it generates these 21 landmarks using a two-step process. Firstly, a relatively fast palm detector scans the entire image and crops out an oriented bounding box containing roughly the hand. This massively reduces the burden on the neural network used to locate the remaining 21 landmarks. Firstly, because the crop box has so many fewer pixels, and secondly, the orientation and scale of the crop box provide a layer of data normalization, which makes the neural network's job much easier. We'll use some of these techniques in the next steps of our own project. OpenCV can be used to directly access the webcam, and the image can then be piped into some classes I built using the MediaPipe hand detector. To add to the stability, I perform a layer of histogram normalization to the image before feeding it into MediaPipe. For those that don't know, histogram equalization is a very common and effective method of fine-tuning contrast within images. This should help normalize for differences between users' webcams and lighting changes too. So the results look like this, and we can see that MediaPipe is doing a pretty good job. I also put in a scaling functionality to the circles so they grow bigger when your hand's closer and smaller when they're further away. You could use this in a number of ways, like controlling the zoom level, but I won't use this at the moment. But if you focus on the exact landmarks, you might see that they're fairly unstable. Now, if you're using your fingers to control a mouse or Flappy Bird's position, these jitters can really deteriorate the gameplay. So we want to smooth the motion out a bit. To do this, I created a container that holds each landmark's previous positions, and then any new position is actually calculated as whatever MediaPipe says, averaged with a number of the most recent past locations. The more past locations we average against, the smoother the result, so I pass this as a user-controlled parameter to the class called smoothness. The result looks a lot better now, and even though with high levels of smoothness you get a reasonable amount of lag, the usability feels intuitive and smooth, and that's what matters most. To finish the model we'll need here, I'll add a Python class that runs the webcam in the background and returns a X and Y coordinate of the index finger that's scaled between 0 and 1. So firstly, let's take a look at Flappy Bird. With MediaPipe able to locate the position of a hand, the game setup here is mostly implementation-based. We can get the background and some graphics from Google Images, allow the bird's X and Y coordinates to be controlled by the scaled X and Y output of the smooth finger detector we've built, and the menu system is just a series of loops, and we put bounding boxes over the selections the user can make. Now, each of these boxes has a timer built into it, which starts counting down from about 1.5 seconds when the cursor is placed within its boundaries, and it triggers a movement to the next menu if the timer hits 0. Pipes are added in as rectangles, and each tick of the game they move an increment to the left of the screen, and we also add in some basic collision mechanics to detect when the bird hits a pipe, which triggers the game over menu, where you can see your score versus the high score, which is just stored as a CSV in the project directory. So moving on to something more complex, which is the gesture game. Building the gesture game is a level more advanced than Flappy Bird in that it uses a feed-forward neural network to determine which gesture the user is making. In other words, while it's great that we can track 21 x and y coordinates of the hand, we need to build some AI to interpret those 21 x and y coordinates and map them to a known gesture such as a peace sign or an OK sign. To do this, firstly, I built an artificial neural network in PyTorch with 2 hidden layers, and the idea here is that it will take 42 inputs, which is 1 x and 1 y for each of the 21 landmarks, and 6 outputs, because I'm going to train it to predict 6 gestures. To get the data, I wrote up a recorder class, which the user provides a gesture identifier, which is like the label we're going to assign a hand gesture. So for example, I use the integer 0 for an open hand, 1 for the peace sign, and so on. And this recorder class records the user for around 60 seconds at a time, recording the 21 landmarks at each frame and saving in a CSV with the gesture label. So it's a general rule of thumb that the more data you have, the better the model will be. So I spent a fair amount of time recording myself making hand gestures, and I ended up with a data set of around 25 to 26,000 labeled unique hand positions. So we train the neural network using this data, but quickly run into difficulties when we test it. Whilst the learning and loss rates look really good on paper, we can see that in practice, the detector fails to recognize the gesture I'm making if I rotate my hand too much. Obviously, the gesture I'm making hasn't changed. This is just because the neural network hasn't seen any gestures oriented in that position inside its dataset. So what we'll do is take a leaf out of MediaPipe's book here and notice that there's no need to augment the dataset by rotating images during the training process, but we can forcibly rotate the landmarks to a predetermined orientation before asking the neural network to make any predictions. So I noticed that the bottom knuckle of my middle finger makes a good up locator, and the base of my palm makes a good down locator. So using some basic trigonometry, we can use a 2D rotation matrix to rotate the landmarks so that orientations are always the same. We also put in a basic min-max scaling normalization just to the scale of the hand, and the result is great. You can see the normalized landmarks in the top left corner, and more importantly, you can see they have complete invariance to rotation and scale. So the same neural network we used before now performs great. So let me show you a quick demo of the gesture game in action. First, we're going to navigate through the opening menus using that box timer that we discussed earlier until we reach the point where we can begin the game. So the game shows an emoji hand that represents the gesture that we need to replicate in order to score a point. The timer counts down, and the goal is to correctly pose as many gestures as you can within the time limit. I added some graphics to intuitively show when the user has got a gesture correct, and I also added a feature that records the prior 5 gesture predictions, only accepting a correct answer if more than 3 of them are correct. This stops erroneous and sudden wrong predictions that can happen on the frame level from ruining the gameplay, and it also increases the stability of the overall mechanism. This becomes a little bit like an ensemble method, because at the high level we're using 5 predictions to calculate 1, which is far more stable than a single prediction would ever be. So all in all, the results of this project are really promising, and they're also extendable to other fields. For example, the gesture detection mechanism would look very similar to the pipeline for facial recognition. MediaPipe also offers facial landmark detection modules. We've seen how important scaling and rotation normalization is to the images and how we can achieve this using the MediaPipe landmarks. Going forward, some of the game mechanics could be improved, and also we could always increase the number of gestures our neural network is trained to recognize. Probably the biggest risk in this implementation so far, which could be addressed, is the gesture dataset, which is entirely composed of gestures I've made myself. In reality, everyone pulls slightly different poses for different gestures, even if it's something really subtle like having the thumb under or beside your 4th finger when posing the peace sign. This dataset should really be expanded to include labeled gestures pulled by a variety of people. With respect to skin tone, I believe that MediaPipe is already trained using a large database with a diverse set of people, so I don't expect this to be an issue. But overall, thanks for listening and happy gaming.